Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Part 22, Field Engineering, Sculpting Light and Force. Remember the language we are learning. There is one field, phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once. Time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and a motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. We are deep in Book 10.4, Reality Engineering. We have built the static stage, materials as frozen phi sentences. Now, we bring the stage to life. We step into the dynamic atelier. Here, we do not freeze patterns. We make them dance. We sculpt flowing rivers of light. We shape invisible hands of force. We paint with sound and energy. This is field engineering. The air in this room is alive with converging beams, swirling vortices of light, and focused points of ultrasound that you can feel as a tiny, intense pressure on your skin. Your new skill is that of the Field Sculptor. You are learning to command arrays of sources, antennas, speakers, laser pixels, not just to emit, but to orchestrate, to make their individual waves meet in space at just the right time, with just the right phase, to weave a desired tapestry of force and light in midair. Scene: the dynamic atelier. The room is dark, but crisscrossed with visible laser beams, green, red, blue, converging, intertwining, forming intricate knots and cages of light in midair. In one corner, a bowl of water sits quietly. Suddenly, a tiny droplet leaps from its surface, suspended in a shimmering point of focused ultrasound. You hear nothing, but you feel a deep, subsonic hum in your bones. On a central console, a hologram displays a 3D map of a pressure field, the silent ultrasound sculpting the air, and an intensity field, the laser light. They are overlaid. You can see the bright focus where the ultrasound holds the droplet, and the green laser vortex threading through it, illuminating it like a jewel. This is not magic. It is coherent superposition. Each laser, each ultrasound emitter, is a single voice. Your console controls their phase. By delaying one voice by a nanosecond, advancing another, you make their waves add up here and cancel out there. You are conducting an orchestra of waves to paint a picture in the medium of space itself. Our puzzle is one of coordination. Given an array of many sources, how do we set the phase of each one so that their combined waves constructively interfere to create a specific, complex pattern? A focus, a vortex, a null, at a target location, even behind obstacles or in a scattering medium. And how do we know we've succeeded? The language role, the orchestration skill. This part teaches a dynamic control skill. It is the skill of shaping a collective wavefront in real time by controlling the relative timing, phase, of its constituent sources. Our core question about phi is, given a target phi of XYZT pattern for a wave field, light, sound, force, and given a known array of sources with known positions, what set of source phases, and optionally amplitudes, will produce that target pattern through coherent superposition? We are moving from writing static sentences to conducting live performances. The anchor image, the choir director. We will use the anchor image of a choir director. The singers, the sources, each have a voice. Singing in unison produces a loud, bland sound. But if the director carefully instructs each singer, you start a little later, you sing this note, you soften here, The choir can produce a complex, beautiful harmony that seems to come from everywhere and nowhere specific. The director's baton coordinates time delays, phases, to shape the spatial sound field in the hall. A phased array antenna, or ultrasound transducer array, is exactly that, a choir of wave sources, and we are the director, using phase to make them sing a focused note at a tumor, or a quiet null at a sensitive ear. The coherent selection principle in field sculpting. In field engineering, coherence is the enabling resource and the source of power. Constructive resonance, alignment, is the goal. All the wavelets from all the sources arrive at the target point in phase. Their peaks align perfectly. This adds their amplitudes, creating a hotspot of intense energy. Elsewhere, we arrange for them to arrive out of phase, peaks meeting troughs, creating nulls of silence or darkness. Destructive resonance, dissonance, is the enemy. Unintended phase errors cause the waves to cancel at the target or create speckle and grating lobes, unwanted bright secondary foci that steal energy and cause collateral damage. The field sculptor's mantra is about precision. If coherence breaks, we stop. If coherence returns, we continue. If the phase alignment across the array drifts due to temperature, vibration, the focus blurs or moves. We stop the emission, recalibrate, and continue only when the coherence is restored. Core mechanisms: beamforming, shaping, and adaptive control. We have a toolkit for sculpting with phase. Phased array beamforming, the director's baton. This is the fundamental technique. An array of many small sources, antennas, transducers, replaces one big source. The phase calculation. To focus at a point P, we calculate the distance from each source element to P. Since waves travel at a constant speed, waves from farther sources must be started earlier to arrive at P at the same time as waves from nearer sources. This time delay is a phase shift. We program each element with its specific phase shift. The result. All wavelets converge at P in phase, summing to a high intensity. Away from P, they interfere destructively. We have steered and focused the beam without moving any physical parts. Wavefront shaping with feedback, seeing through chaos. What if the target is hidden behind a scattering medium, like tissue or fog? The waves get scrambled. Here, we use a guide star and feedback. We place a small reflector or emitter at the target, or use a naturally occurring guide star signal from the target itself. We send test patterns from the array. We measure how the scrambled wave returns from the guide star. Using this feedback, we learn the scattering matrix of the medium, how it mixes phases. We then pre-distort our wavefront with the opposite phase shifts, so that after scrambling through the medium, the waves reconstruct perfectly at the target. This is like the choir director learning the acoustics of a bizarre hall and then instructing the singers to sing wrong notes that, after echoing, sound right to the audience. 3. Holography, storing and replaying a wavefront. A hologram is a frozen interference pattern. When illuminated with a reference wave, it recreates the original object's wavefront. In field engineering, we use computer-generated holograms displayed on spatial-like modulators. The SLM imposes a calculated phase pattern on a laser beam, bending it to form any desired shape in space. A vortex, a multiple spot pattern, even 3D shapes. It's a static phase mask that performs dynamic-looking beam shaping. The coherence criterion, precision phase alignment. Our coherence criterion is strict and measurable. The field pattern is the result of coherent superposition from many sources. The system must maintain precise phase alignment across the entire array relative to the wavelength. This means phase stability. The relative phase between any two source elements must not drift by more than a small fraction of a wave cycle, say lambda over 20, over the duration of the operation. For ultrasound at 1 MHz, wavelength by 1.5 millimeters in water, that's 75 microns of timing error. For light at 500 terahertz, wavelength 600 nanometers, that's 30 nanometers of optical path difference. Amplitude uniformity. Large variations in source amplitude also degrade pattern quality, creating side lobes. We need uniform or carefully apodized excitation. If phase alignment is lost, the focus blurs into a diffuse speckle pattern. The coherent magic is gone. The dissonance indicator, speckle and grading lobes. The primary dissonance indicators are speckle and grading lobes, a grainy, random pattern of bright and dark spots. It arises when phase coherence is present but randomized, as in light scattering from a rough surface or in a multimode fiber. In our context, speckle appears if our phase control is imperfect, or if we are trying to focus through a scattering medium without wavefront shaping. It's the sign of coherent noise. Grading lobes, periodic, unwanted bright spots at angles other than the main focus. They arise from the periodic spacing of array elements. If elements are spaced more than half a wavelength apart, the wave equation admits multiple equivalent solutions, main lobe and grading lobes. They are a direct result of the array's geometry and represent energy wasted in wrong directions. Seeing speckle or strong grading lobes means our sculpting is flawed. The phase pattern we imposed is incoherent with our true goal. The safety rail, diffraction limits and energy conservation. Our safety rail is defined by fundamental physics, not engineering limits. This is crucial to prevent fraud and self-delusion. 1. The diffraction limit. You cannot focus a wave of wavelength lambda to a spot smaller than approximately lambda over 2 NNA, where NA is the numerical aperture, a measure of the angular spread of rays you can collect or emit. This is the Rayleigh criterion. It is a law. Any claim of a super-oscillatory or sub-diffraction focus in the far field is either a measurement artifact, they are measuring something else, or relies on non-propagating evanescent fields that die out exponentially. The safety rail. All field engineering designs and claims must respect the diffraction limit. 2. Energy conservation. You cannot create energy. The total power in the sculpted field, integrated over all space, must be less than or equal to the total power fed to the array sources, accounting for efficiency losses. You can concentrate energy into a small spot, but the spot's intensity times its area is bounded. You cannot create a perfect focus of infinite intensity. The safety rail rule. Any design, simulation, or claim that violates diffraction limits or energy conservation is rejected at the concept stage. We do not waste time on perpetual motion machines for waves. A measurement scene, ultrasound surgery. Let's enact our roadmap's measurement scene. Scene. An ultrasound phased array focusing energy to non-invasively destroy a kidney stone phantom, a model stone in gel. Goal. Create a sharp, intense acoustic focus at the stone's location to fragment it, while leaving surrounding gel, simulating tissue, undamaged. 1. Imaging. First, use the same array in imaging mode to locate the stone. 2. Phase calculation. Compute the phase delays for each of the 256 transducer elements to focus at the stone's coordinates. 3. Safety check. Verify focus spot size is diffraction limited among lambda wide. Verify total acoustic power is within safe tissue exposure limits. 4. Execution. Emit the high power focused pulse. 5. Measurement. Use an acoustic camera, a hydrophone array, to map the resulting pressure field in the gel. The map shows a single, intense hotspot at the target. The gel outside the focus shows minimal pressure rise. 6. Outcome. The phantom stone is shattered. The surrounding gel is intact. Pass. Coherent superposition successfully sculpted a lethal force into a tiny, precise volume. The fail. Loss of coherence. Failure, phase drift. The array's electronics heat up, changing signal delays. The phase alignment drifts. The focus broadens into a diffuse region. The stone is not fully fragmented, and the surrounding gel is heated and damaged. Fail. Coherence broke. Fail B. Grading lobes. The array element spacing was too large. While the main focus is on the stone, a strong grading lobe converges on a nearby point in the gel, causing a secondary lesion. Fail. The design was incoherent with safety. The prediction spine, the hallmarks of coherent field control. A reliable field engineering system yields a clear prediction spine. 1. Diffraction limited performance. The achieved focus spot size will be diffraction limited, is lambda NA. If someone claims a far field spot size 10 times smaller, our prediction is that they are mismeasuring, for example, detecting evanescent fields or using a probe too large to resolve the true pattern. This is a falsifiable prediction. 2. Stability and adaptability. The field pattern will be stable if the environment is stable. If the target moves and we have a feedback loop, like in the ultrasound example with imaging feedback, the pattern will adapt correctly and track the target. The prediction is that the adaptive controller, 10.3.5, will maintain coherence. 3. Gravitational wave thought experiment. As a far-scale lantern, consider sculpting gravitational waves. The equations are similar. It's a wave equation. The prediction spine becomes a limit statement. To produce a detectable, focused gravitational wave signal with a lambda of, say, 1,000 kilometers, you would need to move planetary masses with precise, coherent timing. The required energy is astronomical. This predicts that gravitational wave beamforming is forever impractical, giving us a concrete, humbling limit to field engineering on cosmic scales. Falsifiability, when sculpting, is just spraying. Our falsifiability threads keep us honest about what we're really doing. If claimed field patterns, for example, super oscillatory subdiffraction spots, perfect focusing through thick scattering, cannot be independently verified with calibrated sub-wavelength probes, like a nanoparticle scanner or a fiber optic hydrophone, then they are likely measurement artifacts. The probe itself might be creating the effect, or the measurement is averaging over time in a way that hides the true speckled pattern. If a phased array system cannot focus energy better than a single large aperture of the same overall size, the field aperture equivalent, then the phased array approach adds no value. It's just a complicated, expensive way to make a big speaker. This would falsify the core advantage of field engineering for that application. These falsifiers separate real wave shaping from wishful thinking and technical theater. Triunity in sculpted fields. A sculpted field is a perfect triunity manifestation. We control the timing of each source. This is the direct manipulation of omega at each source. A time delay is a linear phase shift in frequency space. Space echo, the sources are arranged in space. Their positions define the possible K vectors they can synthesize. A large array can create sharper foci. Motion echo, the result is a specific motion of energy, converging to a point, swirling in a vortex, flowing along a Bessel beam. This motion is the direct consequence of the coordinated time and space inputs. Field engineering is the conscious weaving of time and space echoes to produce a desired motion echo. Lanterns across scales, the conductor's baton everywhere. This skill of orchestration applies wherever waves are used. Near scale, optical tweezers. A single laser beam, shaped by a hologram, SLM, can create multiple movable optical traps to hold and manipulate cells, bacteria, or nanoparticles. Each trap is a focused point of light, its position controlled by the phase pattern on the SLM. This is field engineering at the micron scale. Middle scale, 5G, 6G communications. Massive MIMO, multiple input, multiple output, antenna arrays at cell towers use beamforming to create focused pencil beams of radio waves that track individual user devices. This increases data rates and reduces interference. It's a phased array directing information through the air. The Very Large Array (VLA) telescopes use phased array principles to synthesize a giant, continent-sized radio dish. By combining signals from many distant antennas with precise time delays, they achieve incredible angular resolution to image black holes. This is field engineering for listening, sculpting the reception pattern rather than the transmission pattern. The ethics of sculpted force: focused power, focused responsibility. The ethics of field engineering is the ethics of directed energy. 1. Consent and minimization. In medical applications, ultrasound, radiation therapy, the patient's informed consent is paramount. The field design must minimize the dose to healthy tissue. The safety rail of diffraction limits is also an ethical rail. It defines the best possible confinement, setting the standard of care. 2. Containment of application. A phased array that can focus ultrasound to break a kidney stone can also, in principle, focus it to break other things. The containment is both physical, the device is in a controlled medical facility, and administrative, access logs, operator training, usage protocols. The field engineer must design for misuse resistance where possible, for example, hardware interlocks that prevent focus outside a pre-imaged volume. 3. Auditability of the beam. The system must log every firing, the target coordinates, the phase settings, the emitted energy. This creates an audit trail for the beam itself. If tissue damage occurs, one can check. Was the beam correctly focused? This is crucial for accountability. The power to sculpt invisible force at a distance brings the duty to know exactly where that force is going and to ensure it goes only there. The recognition skill, seeing the orchestrated wave. You know you need this skill when you see a system that steers or shapes a beam without moving parts. A radar dish that electronically scans the sky. A smart speaker that cancels noise in a specific spot in the room. A concert sound system that beams clear audio to the back rows without blasting the front. An ultrasound machine that shows a moving focus tracking a blood clot. The moment you see beam steering or wavefront control and understand it's about coordinating many small sources with precise timing, you are seeing field engineering. You are seeing the choir director at work. The master tree location. This part, 10.4.2, is a dynamic pillar of Book 10.4. It depends on 10.2.2, wave vector measurement, to understand the k-space we are manipulating, on 10.3.5, adaptive control for the feedback loops, and on 10.4.0, foundries for the phased array hardware. It is the active counterpart to static material design. It enables the next level of sophistication, topological engineering, where we sculpt fields with stable, quantized defects, vortices, skyrmions. It also directly enables fan-native communication, where we encode information not in amplitude alone, but in the shape of the wavefront itself. This is the control of dynamic fields. Return to the phi. Let us zoom out. The field we are sculpting, whether light, sound, or radio, is a manifestation of phi in that medium. Our array of sources is applying tiny, localized nudges to the phi field. By coordinating these nudges in time, phase, and space, array position, we create a coherent, large-scale interference pattern, a macroscopic phi structure that can carry energy, information, or force along design pathways. We are not creating new waves. We are arranging for the existing universal wave dynamics to produce a pattern of our choosing. We are writing temporary dynamic sentences in the medium of the field itself. Zenodo and the equations of the baton. If you want to see the full mathematical derivations and exact equations behind this idea, you can search for Holophase on Zenodo. There you will find the scientific papers that this audio journey is built on. The papers detail the beamforming algorithms, time reversal, Fourier optics, the rigorous derivation of diffraction limits from the uncertainty principle, the inverse scattering algorithms for wavefront shaping, and the experimental validations of sub-wavelength focusing in the near field and diffraction-limited focusing in the far field. They provide the mathematical score for the conductor's baton. Closing. So, picture yourself back in the dynamic atelier. You command the console. You select a new target in the hologram, a point just above the water surface. You press Execute. Instantly, the intersecting laser beams shift, their convergence point moving smoothly to the new spot. The deep hum changes pitch slightly as the ultrasound focus follows. A new droplet leaps up, caught in the new, shimmering nexus of light and sound. You have just conducted the wave orchestra. You have sculpted light and force in 3 dimensions, in real time. This is part 10.4.2, Field Engineering, Sculpting Light and Force. It is the art of making fields obey your choreography. In our next session, we will add a new layer of sophistication to our sculpting. We will learn to create and manipulate topological defects in these fields, persistent vortices, knots, and textures that cannot be smoothed away. We enter topological engineering. We will learn to tie stable knots in light, create protected channels for sound, and engineer fault-tolerant circuits in the flow of fields. We will move from shaping the wave to structuring its very topology. Remember, one field, phi, with its infinite echoes. We have learned to conduct its rhythms. Now we learn to tie its threads into permanent, robust knots. Salam and peace be upon you.